Oxidative phosphorylation is one of the major contributors of ATP in glycolysis. And to understand the electron transport chain, we will first need to go over redox reactions. And to go over the redox reactions, we will need to first go over the simple mnemonic of oil ring. Oxidation is losing while reduction is gaining. And oxidation is the loss or is losing electrons or hydrogens. Well, and as the name suggests, oxidation is the gaining of oxygen, while reduction, the opposite of oxidation, is the loss of oxygen. And reduction is gaining or is the gain of electrons or hydrogen. If you were to have a reaction between compound A and compound B, where compound B is the reductant, or in other words, the reducing agent. So a reducing agent will force the other compound to be reduced. So B is the reducing agent and A is reduced, or in other words, the oxidizing agent, because it oxidizes compound B. Oxidation cannot exist without reduction. If one molecule is going to donate an electron, there has to be another molecule that will accept that electron. The compound B will donate the electron to compound A. So compound A will be negatively charged. It will gain an electron. It will be reduced. While compound B will lose that electron. Because for any reducing agent to work, it itself has to go oxidation. So in order to make another compound or molecule gain the electron, it itself has to lose that electron. In order to assess a compound or a molecule's capability of losing electron or gaining an electron, we will need to take a look at its reduction potential. So a reduction potential is a compound or a molecule's capability of being reduced, or in other words, its capability of gaining an electron. And the higher it is, or the more positive it is, the more stable the compound is when it actually gains an electron. So one of the most stable ones we have is oxygen, because it has a super high electronegativity. It's in fact the second after fluorine. And one of the molecules most capable of donating electrons is NADH, NADH. And a bit higher up is a compound called FADH2. And these are the ones we will touch on in the electron transport chain. So where does it occur? It occurs on the inner membrane of the mitochondria. So if this were a mitochondria, this would be the outer membrane, this would be the inner membrane, and this would be the intermembrane space. So let's zoom in on the inner membrane. And if we zoom in on the inner membrane, we have the inner membrane here, and we have some enzymes, also called complexes. So we have complex 1, complex 3, and complex 4. Okay, so what we said, we start with NADH, and we would end with the oxidation of, and we would end with the reduction of oxygen. And where will we start? We would start with NADH. So NADH comes in at complex 1 and is oxidized, or it loses an electron. It loses an electron and converts into NAD plus. Okay, so where does the electron go? It goes to coenzyme Q. And coenzyme Q then interacts with complex 3, which takes the electron or oxidizes coenzyme Q. It forces it to lose an electron and donates that electron to another molecule called cytochrome C. And cytochrome C will eventually go through complex 4, which will take the electron from cytochrome C and donate it to oxygen, thus forming water. And that's right here, the protons. At each of these complexes, energy will be liberated because the electron goes from the higher energy state to a lower energy state. Thus, this difference in energy will be liberated. And what will the energy do? It will pump protons into the intermembrane space. So at complex 1, 4 protons are pumped. At complex 3, 4 other protons are pumped. And at complex 4, it's only 2 protons that are pumped. So we've gone over complex 1, 3, and 4. But where's complex 2? And here comes complex 2. Complex 2 is a bit different because it does not utilize NADH. Instead, it is common with the TCA cycle or the Krebs cycle. And we will upload the video very soon, so stay tuned. So here, succinate binds to complex 2 and is oxidized into fumarate. And the electron is then donated to a molecule of FADH, thus converting it into FADH2. And the electron of FADH2 is then donated to coenzyme Q or ubiquinol. And it's a bit different from the other enzymes for one very significant reason. It does not pump any protons. Let's name each of these complexes. Complex 1 is NADH ubiquinol oxidoreductase enzyme. And here it's succinate dehydrogenase enzyme. And if we lose hydrogen, it is losing of hydrogen. It's oxidation. So succinate dehydrogenase oxidizes succinate. And here complex 3 is coenzyme Q or ubiquinol cytochrome C oxidoreductase enzyme. And complex 4 is cytochrome C oxidase enzyme. So we've said in the beginning of the video that the ETC or the electron transport chain is one of the major contributors in glycolysis. However, we haven't touched on ATP anywhere on this board. Let's say we have the inner membrane of the mitochondria here, and we have our complexes, complex 2, complex 3, complex 4. So here we pump 4 hydrogens, or 4 protons, and 2 protons. And on the inner membrane there is a membrane potential, also called the mitochondrial membrane potential, where the intermembrane space is very positive because of all these protons, while on the matrix side it's very negative. And here comes in a new enzyme called ATP synthetase. ATP synthetase. And ATP synthetase is very interesting because the inner membrane is impermeable to protons. So the protons on the outside cannot diffuse back into the matrix. They have to go through ATP synthetase. And ATP synthetase on the matrix side binds to ADP, adenosine diphosphate, and inorganic phosphate. So when the protons cross the ATP synthetase, they cause the enzyme to mechanically rotate. And this mechanical rotation causes a conformational change that causes ADP to bind into inorganic phosphate, causing the formation of ATP, adenosine triphosphate, which is the, as you may recall, the energy currency of the cell. So, how many ATPs do we gain from this? In a very efficient cell, or a cell where NADH and FADH2 are only utilized for ATP production, each molecule of NADH would result in about 3 ATPs, 3 ATP molecules. And each molecule of FADH, or succinate, will result in about 2 ATP molecules. So, let's go over some drugs that interfere with the electron transport chain. So there are very important classes. So let's start with, for instance, something called a decoupler. Decouplers such as DNP, dinitrophenol, are molecules that are very weak acids, So these weak acids bind to protons, and then they diffuse into the matrix, and then they release protons on the inside of the matrix. This causes protons and less protons to go through the ATP synthetase. Thus, they decouple or disconnect ATP synthetase from the rest of the electron transport chain. because the inner membrane is now more permeable to protons, so it can just cross the inner membrane without ever going through ATP synthesis. There are also different types of inhibitors, so we will focus mainly on inhibitors of complex 1, 3, and 4. So, we've said before that there are decouplers, or such as DNP, which is currently used as an insecticide and illegally used as a supplement to lose weight. And it's very dangerous because, well, it's used, and there is a reason it's used as an insecticide, don't you think? So, there are decouplers, first of all, and for complex 1, there is retinone, amytal, and MMPs. So there are MMPs, retinone, and amytal, and all of these are complex 1 inhibitors. In complex 3 inhibitors, there is only one very significant one, which is antimycin A. And complex 4 inhibitors are plenty, such as carbon monoxide and cyanide, which are very toxic, by the way. And most of these are toxic, so they aren't really used much, with the only exception of one sedative, which is amytal. So it's a sedative and hypnotic.
There is a fifth class of inhibitors called ATP synthetase inhibitors. These inhibitors work by blocking the proton channel of ATP synthetase, thus blocking the passage of any protons that cause the rotation of ATP synthetase. Therefore, no production of ATP occurs. Another thing I didn't mention is that uncouplers produce heat because they reduce the amount of protons pumped through each complex, and thus more energy is liberated in the form of heat. They also prevent the formation of ATP, which prevents the formation of any bonds that store energy. One very good example of this is thermogenin, which is brown fat, which is utilized by the body to produce heat when the body is cold. And also, I didn't mention the definition of phosphorylation. Phosphorylation is the addition of a phosphate group to any molecule or a compound. For instance, transforming a nucleotide diphosphate to a nucleotide triphosphate. For instance, ADP to ATP. Or the addition of phosphate to a protein or an enzyme. In general, it does alter its effect, which may inhibit it or increase or activate the enzyme.
I hope you guys enjoyed this video. If you like it, please subscribe and like. If you have any feedback, please leave it in the comments, and see you later.